Should we start? Maybe we'll start. So, let's take a status where we are, because we're not quite finished yet. So far, this is what we have talked about. We spent the first lectures on trying to answer the question, what's really going on here? So we looked into the machinery of inverse problems by means of the singular value expansion, the singular value decomposition, in order to understand why they are difficult and what it is that that creates the difficulty. And then we talked about what to do about that, what to do about the amplification of the noise, and that led us to discuss various regularization methods, for example, truncated SVD, Tikhonov regularization, and so on. So that's handling the difficulties of inverse problems. But there's still, you have to choose a balance between essentially trusting your data, fitting your data, and imposing prior information about the solution, for example, smoothness. So how much regularization do you have to do? And that led to this discussion about methods for choosing the regularization parameters. So there was like a discrepancy principle and generalized cross-validation and so on and so forth. So that's all very good. So in principle now you can handle inverse problems, right? So we are almost done, but many of the methods that we have talked about here are pretty good for dealing with problems that are not too large. But once we get to larger problems, we have to look in other directions to arrive at methods that can be used in practice. So that's what this slide here is about. So most of the exercises, I guess, in this course is up there in the first category with really small-scale problems where basically we can do anything. For example, we can compute the singular value decomposition because the matrices are so small, and once we have that, we can compute a lot of different regularization methods simply by plugging in the singular value decomposition. So that's very nice. Such small problems is something that you never see in practice. That's something you see in the textbook, right? So we also have to look at larger problems. So if you go to problems that are somewhat larger than the textbook examples, then suddenly you can no longer really ignore the computing time for doing your computations, and also there may be alternatives to the singular value decomposition that are more efficient, maybe QR factorizations if the matrix is sparse. You know, there are a bunch of numerical methods that can handle with sparse matrices and so on and so forth. So that should be taken into consideration there, that maybe the singular value decomposition is not what you really want to do. And then for what I call here large-scale problems, that are probably the kind of problems you really encounter in applications where you collect a lot of data and your reconstruction is two-dimensional or three-dimensional. Then suddenly, you really have to think about what you do. Computing factorizations, singular value decomposition, QR factorization, stuff like that, is not really possible any longer just because of the size of the problem. And on top of that, you really have to be aware of storage requirements and computing time and so on. And then, of course, there are certain problems where you can utilize the matrix structure to arrive at fast algorithms that can be based on n log n algorithms, such as the fast Fourier transform. But if you're dealing with more general problems with no such structure, really it seems the way to go is to use iterative methods. Okay, and so that's what I'm going to be talking about today. I'm going to explain to you what I mean by iterative methods. So what is an iterative method? Well, it's a method that produces a sequence of iteration vectors. You have to choose a starting vector. Very often that might be just a 0 vector, but it could be something else. And then it produces this sequence of iterates, and hopefully they will converge to the solution that you're interested in. In the case of inverse problems, you want this to converge not to the naive solution, but to a regularized solution. Right, so that seems a little bit tedious that we have to do this. But the thing is that with iterative methods here, we can completely avoid doing factorizations. We only need the coefficient matrix A in matrix vector multiplications. Typically, you need to be able to multiply with both the matrix and the transpose. Right, that's the only thing that's where A comes into play in these algorithms. You just multiply with it. All right, and that means that for many problems, you may not even want to store the matrix, maybe as a sparse matrix. All you need to do is have available two black box functions that can compute multiplication with either A or A transpose, right? Do that on the fly without actually forming the matrix and storing it. Just do the operations inside that function that corresponds to multiplication with A and A transpose. Right. So that's quite important actually, because then you don't have to worry about the storage anymore for that matrix. And some of these computations can be done very fast on modern computer architecture. And the building blocks for all this is really very, very simple operations. It's the matrix vector multiplications, and then there is Saxby operations, which is a vector plus a scalar times another vector. There's the 2-norm computations. Very, very simple operations. They're also easy to do on a modern computer. And then the thing is that, and this is what we're going to be utilizing in the methods that I'm talking about today, is that this sequence here of iteration vectors, 0, 1, 2, 3, 4, and so on, produces solutions that actually tend to look like regularized solutions, and we'll have a look into that, why this is so, because that's a bit amazing actually, that you just run such a simple scheme there and then you get a regularized solution. So we will look much further into that. But just to set the stage here, when we talk about iterative methods, there really are two kinds of two ways of thinking about using iterative methods in this context here. One is that you basically set up a regularization problem. So this could be Tikhonov regularization in general form, for example, and we know that's equivalent to these kind of regularized normal equations there. And then you apply your favorite iterative method to solve that linear system of equations up there. So that could be maybe conjugate gradients or other Krylov subspace methods that are very suited for that. The difficulty there is that if you want these methods to run really fast, you actually need a good, sometimes you need a good preconditioner. And designing a good preconditioner to accelerate the convergence of these methods for these Tikhonov problems is quite difficult in many cases. So it becomes very problem specific what you're going to do there. But anyway, assume you can do that, then your iterative method will, of course, if you apply that to the Tikhonov problem right there, the iterates will converge to the Tikhonov solution, right? Okay. Another disadvantage there, of course, is that if you're not quite happy with your regularization parameter lambda, and you want to try another lambda, because maybe that would be better, then you have to start the iterations from scratch again. You have to run the whole sequence of iterations for every lambda, basically. So it can be quite tedious if you don't know what's a good lambda. Right. So I'm not saying you shouldn't do that, but it can be a bit overwhelming sometimes. So I'm going to today talk about a different approach, which at first seems really, really weird, and that is we pick our favorite iterative method, and then we apply it to the problem without regularization, and then we see what happens. So that seems a really, really strange thing to do, because we have spent so much time looking at what are the difficulties and why is it that we really need to do regularization. It's mandatory in order to compute a good solution to these noisy inverse problems, and yet here I am telling you that just apply your iterative method to the unregularized problem there. So what's going on here? Well, the thing is that we'll be relying on something called semi-convergence. Right. See, asymptotically, our iterative method will, of course, converge to the naive solution to the unregularized problem, and we certainly don't want that. But the thing is that in the initial iterations, these iteration vectors actually tend to move to somehow approach an approximation to the exact solution. That's the one we're really interested in. And then later on, it'll start to diverge from this guy here, again from x exact, and then converge to x naive. All right. So we just have to stop the iterations. Before that happens, we have to stop at towards the end of the first stage of the iterations. So basically, that is the situation here. This is how one can view an iterative method. So here this white space here is our vector space Rn, and any iteration vector is of course a point in Rn. So it's one of these colored dots there. Right? So what do you do in an iterative method? You pick a starting vector that could be the 0 vector or something else. So you will be there. And then you produce a sequence of iterates by means of your iterative method. No matter what iterative method it is, you will produce a sequence of iterates. And they will wander around in your space, go around, and eventually, they will converge to the naive solution, the one we have over here with the red dot over here. It'll converge to that one, except we don't want to go there. Okay, but eventually the method will converge over there. But here's the interesting thing, though. Before it gets over here, before it reaches the naive solution, very often these iterates will come close to the exact solution, which is we have seen that, of course, the exact solution, the one that corresponds to no noise, is pretty far away from the naive solution. So it's down here. That's the blue dot there. And in this particular example here, actually, for a certain number of iterations, we are pretty damn close to the exact solution. And of course, we want to stop right there before we continue. And then, how do you know when to stop? Well, we'll see that the number of iterations plays the role of a regularization parameter. So we actually have these parameter choice methods that we have talked about already. And so we will use them as stopping rules for the iterations. So to some extent, we know how to handle that question of stopping. But what's interesting is how does this work in practice, and in fact, why is it that we have this peculiar behavior here, that we actually along the way get a good approximation to the thing we really want? So we have to look into the details of this. And to do that, we're still going to be using the singular value decomposition, but here we use the singular value decomposition as an analysis tool, certainly not as a computational tool, but just a tool for somehow analyzing what's going on, so for the theoretical understanding of what's going on. Okay, so we will start with one of the most simple iterative methods, probably, for solving the unregularized least squares problem, and that's the Landweber iteration. So that's the top equation right there. So you see, at any given time you have an iteration vector xk after k iterations, and how do you then progress to the next iteration vector xk plus 1? Well, xk plus 1 is xk plus a correction here. So let's see, in the parenthesis b minus a xk, that's like the residual corresponding to xk. Then you multiply with a transpose, and you multiply with a scaling factor there, so-called relaxation parameter, that sort of controls how fast you converge. And but you have to be a little careful with that. You can't choose omega of arbitrary size. Of course, you should be greater than 1 if it's than 0. If it's equal to 0, nothing happens. But it can't be too big. That's what I'm saying here. So there's an upper bound on omega for this thing here to converge. Right. So what this method is doing is actually it's solving the unregularized least squares problem. So it's often called Landweber, but it's also called, in optimization, it's called the steepest descent method. So that's what it is. All right. And you can derive it by writing up, the equations here for the derivative of this objective function there, and so I'm not really going to do that, but that's the Landweber method there. And various variants of this are actually used very often to deal with inverse problems. So anyway, instead of deriving that, let's see what it's doing. So here's a very, very simple 2x2 system of linear equations. And of course, solving a 2x2 linear system of equations, the geometric interpretation of that is finding a point here in R2 where both equations associated with the linear system are represented. So the first equation, the first row of the matrix together with the first element of the right-hand side, they define a line here in R2, and the second equation in the linear system defines another line. And if the matrix is non-singular, the two lines are different and they intersect just in one point. And where they intersect, that's the solution to our linear system of equations. Okay, so what I'm showing here is a typical behavior maybe of the Landweber iteration. And I think I start with a 0 vector. So I start somewhere outside the picture. And then you can see in the beginning, I have quite some zigzag behavior of the algorithm. You see, it starts down the outside the picture, and then it takes a step, and it shoots outside of the picture again, on top of the picture, and then it goes down again, it goes up again. But after not so many iterations, it seems to behave itself and somehow stabilize, not do so many of these large oscillations. And at the same time, these iterates are slowly progressing towards the solution. I hope you can see that. So after 30 iterations, you can see I'm on my way there. So that's interesting. What's going on there? Well, what we're going to do is, of course, apply analysis in terms of the singular value decomposition. And of course, so I guess I need to write that here on the blackboard. So we have seen many times that the regularized solution, we can write that in terms of the of the singular value decomposition in this way here. That's what we got here. We expand the regularized solution here in terms of the right singular vectors, and then we have some coefficients here, the right-hand side coefficients divided by the singular values, and then there are some filter factors here, and for every regularization method, there's a specific set of filter factors that you plug in here. And remember, the role of those filter factors is to somehow get rid of those SVD components that we don't like and keep the ones that we like. Okay, we want to filter away the noisy SVD coefficients. So that's a very, very general way of writing up a regularized solution. So what here specifically? Well, now we are looking at the case iterate. So I'll give it a superscript there. So now we are looking at the case iteration vector, the vector after doing k iterations of our iterative method, and in this particular case, Landweber. Okay, so of course, we also have to add that subscript here to the filter factors. So for every iteration, there's a new set of filter factors that you plug into that equation. And if we want to understand what's going on and why does this work, the only thing we have to do is that we have to work out what are these filter factors. If we can do that, then we pretty much understand what's going on. So it turned out, and again, I'm not going to derive it, I'm just going to give you the result. But after k iterations, these filter factors have this particular expression there. And see, there's a subscript I, because there's one filter factor for every SVD component. And you can see they depend on, well, they depend on the relaxation parameter omega. They depend on the number of iterations k. If those parameters were not in the equation, I would have made a mistake, wouldn't I? And then, of course, there's also the singular values. You see them there. So you can stare at those equations there for a little while, or you can plot them to see what's going on, and that's what we do here. So again, these are the filter factors for Landweber iteration. All right. So what are we plotting here? Well, along the first axis here, we have the singular values, and just think about a situation where there are like really, really many singular values. So when you plot the corresponding filter factors here, it looks like a continuous line. Anyway, so those are the that's how the filter factors, how they depend on the ith singular value. All right. And let's look at let's look at the solid blue line there. Those are the filter factors for the case where our relaxation parameter is equal to 1, and we've done 10 iterations. So that would be this line here, the thick blue line here. So what does that tell us? Well, it tells us that after 10 iterations, some of the filter factors are close to 1, and those are the filter factors that we see up here, and they would correspond to singular values in the range, let's see, maybe greater than 1/2, something like that. So if you have singular values greater than 0.5, then the corresponding filter factors are equal to 1. So that means these singular values in this range here will essentially be included in your regularized solution after these 10 iterations. And singular values over here, smaller than that, they're pretty much stamped because the filter factors here, they just get smaller and smaller. These filter factors really, really look like Tikhonov filter factors. They're not quite Tikhonov. It's a different expression, but they behave in quite the same way. Some SVD components are kept because the corresponding filter factors are very close to 1, and then the small singular values correspond to small filter factors that dampen those contributions. All right. Okay, so already that's interesting. This is doing the same thing as truncated SVD and Tikhonov. It's keeping the large SVD components and filtering away the small ones. All right. Okay, let's do some more iterations then. Now the green dashed line, those are the filter factors after 20 iterations, so twice as many iterations. And you see basically that curve is now shifted to the left. So there are a few more filter factors that are now close to 1, and then they start decaying. So what that basically means that after some more iterations, you have effectively included some more SVD coefficients in your solution. So that's all right. Let's keep doing this. So, and the next two lines there, the red one and the bluish there, corresponds to 40 and 80 iterations. And every time we do more iterations, you can see we include more SVD components with full power, but we're still filtering away the SVD components corresponding to the small singular value. So that's basically what we see here. So there's filtering. There's definitely filtering going on, and the number of iterations is our regularization parameter. The number of iterations basically determines how many SVD components that we are including in the solution. So that's pretty cool. You know? So this hints at what we should do. We should just keep running the iterations until we just have the right amount of SVD components included in our solution, and then we stop there. Just like with truncated SVD, we just keep adding more and more SVD components until we are happy with the solution. So it's basically the same thing. Except we don't need to compute the singular value decomposition here. We just have to run these. I'm backing up here to slide 5. These very, very simple Landweber iterations there, where you see all you need to do is to do some matrix vector multiplications and a bit of linear algebra there. All right. So let's look again at this plot of the filter factors. Yeah, forget about the thin line there, but there are some black circles there, and I'm tracking a particular point on these curves here, and basically what I'm trying to say here is that somehow if we define that you know the filter factors above these dots are large, and the ones below them are small. That's quite a bit arbitrary. But what's interesting is that how does this black circle here move to the left? Well, it certainly seems that it's in this double logarithmic plot that it's moving the same distance for these four curves there, and so what's the difference? When in the first curve I've done 10 iterations, then 20, and then 40, and then 80. Okay, so what this is trying to tell me is that every time I double the number of iterations, then the curve moves to the left with a constant factor. It's got to be a constant factor because this is double logarithmic, right? And yeah, the bottom equation here on slide 7, that's what there's a mathematical expression that actually tells us what this factor is, and it's essentially a square root 2. So yeah, I'm not going to go through that, but the important message is right here on this plot here. As you do more and more iterations, you gradually incorporate more and more SVD coefficients in your solution by means of the filter factors behaving in this particular way. Right. So that's quite nice. Actually, it justifies that we really have this behavior. Now I back up to slide number 4. Here again, illustration of the semi-convergence. Right. So if we look at the iterations here, doing the first iterations here, we are really, if this was a Landweber iteration, we'll just be incorporating more and more SVD components into our iteration vector. And right at this point here with the optimal number of iterations, we have incorporated just the right amount of SVD coefficients or SVD components that we want. And if we go beyond that, it's completely the same thing with truncated SVD and Tikhonov. Then the noise starts to come into our solution, and of course the iterates will then start to diverge again, right, from the optimal regularized solution, which is right there at the bottom. So I hope that gives you an sort of an intuitive idea why we can actually obtain regularized solution in this way here by applying our favorite iterative method to the unregularized solution. It's the number of iterations doing the job here. Well, I quite like that. Yeah. I'm going to cover a few more basic iterative methods and then we'll take a break, because I do want to mention another popular iterative method. It's called the Chimino's method, and it looks very much like Landweber, doesn't it? But if you look carefully at that iteration right there, you will see that here there's a D matrix sitting right there. That's actually the only difference. There's a D matrix there. That's a diagonal matrix, and the diagonal elements of that matrix are defined in this way here. Right. That's how I define them. So essentially, 1 over the squared 2 norms of the rows of the matrix A. And in this notation here, in my notation, there's also a factor 1 over m. In some papers you see that factor, in other papers you don't see that factor, but it's not so important because that factor could be absorbed actually in your relaxation parameter omega, so that's not important. What's important here is this nature here of the D matrix, which essentially scales the problem relative to the norm of the rows. And in many applications, that's actually a good idea. Yeah, that's actually a good idea. In fact, let me jump ahead a little bit to slide number 12. So you can see that just this simple scaling there, you have to create the D matrix once and for all. That's the only thing. You have to scan through your matrix, compute the row norms, store them, and that's it. And then apply them in every iteration. But you can see in this plot here, it really matters. Along the first axis here, we have the number of iterations. And along the second axis here, again, this is a logarithmic axis here, that plots the relative errors in the solution, and this is for a particular test problem that I don't recall what it is. All right, and then you can see Landweber. Landweber is not famous for its convergence. Actually, it's pretty slow convergence there, you can see. And if we switch to Chimino's method instead, which is just incorporates a clever scaling, then suddenly you see much faster convergence, especially in the beginning. So it's worthwhile thinking about stuff like that, all right? And yeah, I'm going to talk about one more basic iterative method before we take a break. Yeah, and that is Kaczmar's method, yeah, which was developed in the 30s as a method for solving linear system of equations. It's been rediscovered several times, and probably the most important rediscovery of that method was by Gabor Herman and his colleagues in New York. And so they described that method there from a more practical point of view as a method for doing image reconstruction. So that was one important contribution. The other important contribution of the paper was that they found a very cool name for the method. They called it the algebraic reconstruction technique, or ART. And that's a really good idea because no one can pronounce Kaczmar's, right? And nobody can remember how to spell it. Often I'll be calling this the ART method because I can spell that. Okay, so again, we are working with the rows of A and the iterative method. If you write it out, looks like that. Well, basically what it does, if you look at the equations there, is that you can see sequentially we involve one row of the matrix at a time, starting from the top and then going to the bottom. And once we're done with that, we start from the top again. So cyclically we're involving the rows of the matrix A, and then we do something. And this something, what is it we do? Well, we can see it here on this plot here. Forget about the red and the purple lines there, but you see here, again, I start in the 0 vector, and then what's going on here with this method, it has a very, very simple geometric interpretation. Again, I have a blue line and a green line. Those are the two lines associated with the 2x2 linear system of equations that I'm trying to solve, and of course my solution, again, is right there where they intersect. What I do in every iteration is that I project the current iterate onto one of these two lines in a cyclic fashion. All right? So my first step is an orthogonal projection of the point here at the origin. Orthogonal project that onto the blue line, and then I end up right there. All right? And then I project that point orthogonally onto the green line, and that brings me up here. And so I do that repeatedly through all the rows of the matrix, but I only have two in this case here. So now I'm going to start from the top again, and I orthogonally project onto the first equation, and then on the second equation I keep doing that. So that's what's going on. That's a simple geometric interpretation of that. And we hardly need a proof that this will converge, because it'll just be zigzagging its way until we hit the intersection there. Actually, we do need a proof, because it might actually zigzag forever without getting to the solution. But trust me, it actually converges to the solution right there. So that's Kaczmar's method. And yeah, so here we cannot really do an SVD analysis, but we can look at this plot here and probably convince ourselves that this is also this is doing the job, right? Right, so these were some very, very simple iteration methods. I back up here to the description of Kaczmar's again. They have been used for many years. This method here people started to use this back in the 70s, and I think one of the reasons why people like the method like this one here is that it has quite low memory requirements. You don't need to work with the whole matrix. In every iteration here, if you look at the inner iteration, all you need to bring into memory is, okay, you've got to have your x vector and an element of your right-hand side B, and then one row of A. And back in the days, that was pretty much what you could store in your memory. So probably that was one reason why this was quite popular in those days. And the second reason, which is certainly also very important, is that out of the three methods we've been talking about here, the ART method is certainly the one that has the best convergence, the fastest convergence, especially in the beginning here. It's reducing the error quite dramatically until a certain point after, say, 10 iterations, and then it's not really making more progress. But even after 10 iterations, it's doing much better than the other two methods. So that's another reason why we like the ART algorithm, because it's got an impressive convergence, especially in the beginning. Right? So those were the basic iterative methods. And we're going to take a break now, and then we will be talking about some other